Okay, test 5, the tower test. Now this part is really for propagation experts, and it's a kind of geeky, so skip to the end if you're not interested. It's not exactly propagation model validation, but it does relate to the model, and it's so damn interesting and unique, I want to include it. I'm not sure anybody else has ever done measurements like this. If they have, I've never heard of it. Okay, back to the asphalt test range. I was thinking about the noise which is present at long range in all the data sets. Here's the flat asphalt test set from the beginning of the video, and let's zoom in on the long range part. We can see that the spatial noise has overall a bigger variation from point to point than the time variation at any single point, broadly speaking. So what's causing the spatial noise? Well, maybe it's some strange effect caused by road surface reflections that just shows up at long range. Or maybe it's coming from the off-axis scatterers like the trees. We can check if it's coming from the trees by relocating the transmitter from the road to a tower 160 meters opposite the road center line, and then perform the measurements along the road center line in the usual way. Then we move the transmitter on the tower deck and repeat the measurements. So here's the rationale behind this experiment. Think of the transmitter in trees as a very large multi-element array having a length of about 150 meters. That's the distance from the tower to, let's say, the center of the trees. And the trees behave like, let's say, like passive antennas. So that array length is about 450 wavelengths at 900 megahertz. And since the array is so large relative to a wavelength, the radiation pattern will have a high angular frequency, especially since the receiver all along the center line of the road is well within the Fresnel region of the array. Now, if the scatter from the trees is a significant contributor to the signal at the receiver, then we should be able to change the received signal at every point on the roadbed by scanning the radiation pattern of the transmitter and the trees in azimuth over the test area. The radiation pattern can be scanned in azimuth by moving the transmitter on the tower slightly further away from the test range. Since the array length is so large, a small change should cause a noticeable change in the measured power all along the test range. And if the trees are not a significant contributor, then moving the transmitter further away from the test range by a small distance will make little or no difference in the measured power. Maybe it looks like this. It's a simulation where there is very little difference between the results for the two transmitter positions. Now, it's not quite as simple as I make it sound because there are ground reflections throughout, but that's the hypothesis that the experiment will test. And here's a graph of the first measurement set, power versus range in a straight line along the asphalt road, along the center of the road. So if the hypothesis is correct, then the spatial and temporal noise are caused by reflections from the off-axis trees. And if the trees weren't there, we would expect to see a nearly constant power since the receiver was moved cross-range relative to the line of sight to the transmitter. So there's hardly any radial change at all, or almost none, between the transmitter and the receiver. Here are the results when the transmitter is moved 1.675 meters toward longer range, that is, away from the receiver track line, away from the road. The results are similar, but different. The mean values are noticeably different, and at several points, the difference between the means is greater than the variation of either signal. That's the evidence which partially supports that the hypothesis is correct, that the long-range spatial noise seen in all the measurements is caused by off-axis reflections. The bottom line is that because of these measurements on balance of probability, I believe that the spatial noise is due to off-axis scatterers in the environment.
In conclusion, based on the experimental results presented in this video and a whole bunch more that don't fit in this video, I believe that the propagation model is correct as it applies to these tests. Now, whether it applies under conditions for a missile attack at sea, I have to volunteer that's an open question. That said, there's nothing in the math model that would be peculiar or particular to 900 megahertz versus X-band or Ka band or Ku band. What we have to do is swap the reflectivity of asphalt for the reflectivity of seawater and then adequately represent the shape of the sea surface as it would be experienced, as it would exist in an actual missile attack. And then we take the predictions, the model predictions, and compare them to real-world at-sea measurements with a plane and a missile seeker and a jammer on board a ship or elsewhere, and see how it stacks up. And this concludes a presentation about why I believe the propagation model is valid for our study of ship defense against missile attack and specifically jog detection.